morning. Welcome to a new presentation of Chemforum. Today we have a pleasure of welcoming Professor Teresa Avilés. Professor Teresa is graduated in chemistry by the University of Murcia. In the 1978, Professor Teresa received a PhD at the Oxford University under the supervision of Professor Green. Since 1983, is Professor of the Department of Chemistry of the Faculty of Science and Technology of the University of Lisbon in the area of inorganic chemistry. The research interests of Professor Teresa are coordination and organometallic chemistry and homogeneity parameters. Professor Teresa is author of the 47 publications, supervisor of the 3 PhD theses, and the principal investigator of several projects. Today, Professor Teresa will talk about copper complex bearing these amino acids and ligands for catalysis. Welcome, Professor.
Okay, well, first of all, I would like to thank the organizers for inviting me to give this seminar. And then I will talk about copper complexes bearing these imino acenaphtene BIAN ligands for catalysis. Well, copper is a group 11 metal, and coinage metals is the name of the group, and usually appears in 2 coordination states, which is copper 1 and copper 2. Copper 1 is a D10 electronic configuration, is diamagnetic, and copper 2 is a D9 and is paramagnetic. The symbol in alchemy is the female symbol. So when I found that, I was very surprised because I didn't know it. And I tried to find why the copper is associated to the female symbol. And this is due to the word copper that comes from cuprum, from Latin. And cuprum means from the island of Cyprus. And from Cyprus also comes Aphrodite and Venus. Therefore, the goddess of love and beauty and the female symbol for the Greek and for the Romans. Also, copper is known since a very long time ago. There are archaeological evidence for at least 11,000 years. And is also an essential element in the human body. The percent per mass is less than 0.05. And the word production is represented here, is quite abundant in the Earth crust, is 0.0068%. And the country which produces more copper is Chile, with 34% of the world production. Well, before I start my talk, I would like to acknowledge the people that are involved in this work. And then the person that is being involved more in this work is my collaborator, Pedro Teixeira Gomez, and his group, he's present in the audience. And then Li Dong Li, that was here for a period of time, he was very much involved in this work. And Teresa Duarte also, with all the X-ray structures determination, that there are quite a few. In my department, in the chemistry department, that is represented here, in the chemistry department, there are 3 doctors already, that is Vitor Rosa, also present in the audience, Christoph Fliedl, and Carla Santos. Okay? Well, I would also like to thank FCT for financial support. Well, for the people, most of you probably know where the chemistry department is in the campus of the Faculty of Science and Technology of the UNL on the other side of the river. Well, I will start then with copper. Copper has many applications. For instance, there was a volume of organometallics that was entirely dedicated to organocopper chemistry. This is the volume of organometallics, and it was entirely dedicated. So there are many applications of copper complexes for catalytic reactions. And I will talk about two of them, okay? The first one I will talk is called the Huisgen 1,3 dipolar cycloaddition reaction of acids and alkenes. The abbreviation for this reaction is copper AAC, okay? And this reaction consists in the reaction of an acid and an alkene to give a triazoles. If you do the reaction without the copper catalyst, you get a mixture of two isomers. For instance, by heating these two reactants, you get a mixture of isomers, is 1,5 isomer and 1,4 isomer. But if you do it in the presence of a copper 1 catalyst, you get selectively just one of the isomers, the 1,4 isomer. Therefore, this is known as a click reaction and is regarded as the best click reaction known to date, okay? The term click was coined by Sharpless and co-workers in 2001. And I will talk a little bit about what is considered a click reaction. A click reaction is considered a near-perfect bond-forming reaction. So this is represented here. You have two moieties, and it's like a click, okay? They come together, and they form a bond. For being a click reaction, they should have a high yield. They should be reactive in ambient conditions. They should use benign solvents. It should have a fast reaction kinetics and minimal or inoffensive byproducts. Okay, these are the characteristics of a click reaction, of which the one I will talk about is considered the best click reaction known to date. Okay, so I will start with the acid alkene to give the triazoles with a copper 1 catalyst. The copper 1 catalyst we use are based in the BIAN ligand, which is represented here, and they can be cationic or neutral copper 1 complexes, okay? So we started by synthesizing the copper 1 catalyst. And we did, with Pedro and I, lots of copper 1 compounds. And we did, for instance, the synthesis was based in the ligand plus the stoichiometric amount of the copper 1 salt. In this case, is the tetrakis acetonitrile copper 1 of another nitrile, for instance, benzonitrile. And with the stoichiometric amount, you could get the bischelated complexes or the monochelated complexes in which you have two nitriles joined, coordinated to the copper, okay? So we did a lot of synthesis modifying the R substituent by, for instance, 2,6 isopropyl, 2,4,6 trimethyl, and we did also these monochelated complexes. If we, instead of having nitriles, we wanted to have another ligand, then we put it in the reaction mixture, like in this case, the triphenylphosphine, and then we get the triphenylphosphine. These syntheses were not difficult, and we could get, in most of the cases, we could get single crystals. For X-ray structure, for instance, there are two examples here of bischelated complexes. In this case, is the 4-isopropyl here in the arene of the BIAN ligand, and here is the 2-isopropyl. So these are two bischelated complexes, and the copper center is always in a distorted tetrahedral geometry. So this is a characteristic of all these complexes. Copper is always in a distorted tetrahedral geometry, as it's seen here, okay, with the angles, and in this case also. Here, there are represented the mono-chelated complexes. In this case, is with the benzonitrile, and in this case, with the triphenylphosphine. Okay? We continue synthesizing all kind of complexes. In that case, changing the R substituents by, for instance, 4-isopropyl, 4-methoxy, 4-nitro, 2-isopropyl. In this case, with chelating diphosphenes, and even with ferrocene. And we tried with stevine and arsenes, and with these routes, we couldn't get the results. So we already had quite a large amount of cationic copper-1 complexes. Here, for instance, is the arsine with 2 arsenes, and with the 4-isopropyl, like you can see here. And then we synthesize some neutral complexes. The neutral complexes were of this type, starting with the ligand. This was with the first route is using copper chloride or copper iodide, and we got this type of monochelated copper-1 complexes. And in this case, we have dimers, and in this case, we had a mixture of dimers and monomers. So we have all this with different substituents, for instance, a library of different copper-1 complexes. The reason was that we wanted to use them as catalysts, and we wanted to see how the stereochemical characteristic of the R substituents or the electronic properties will affect our results in catalysis. Here, the X-ray of the dimer with an iodide bridge, and the monomer with a phosphine and a chloride. Okay? Well, then the catalytic reactions were performed by treating phenylacetylene and benzyl azide in the presence of the catalyst and getting this triazole product. And then with the compounds we treated, we found that one of the best catalysts was the one with the bis triphenylphosphine. In this case, we have this, the reaction time was 36, 24, at temperatures of 20 or 50, and we had 100% yield. And here are the tone and TOF characteristics. So that was our best catalyst for this type of reaction. Therefore, we came to the conclusion, since the bischelated were worse catalyst and the monochelated were better catalyst, we came to the conclusion that there was an equilibrium in which there was a dissociation of the two ligands or one of the RBN ligands, and then the dissociated product will be the starting point, and then by some way, we didn't look very much at the mechanism, but it will add the alkene and the acide and give the triazole. So we thought that the first step will be the dissociation, and that was the reason why the bischelated were worse catalyst than the monochelated. Well, this was published. That was our first publication in 2012. And all the people, of course, that I did not mention at the beginning, but they were all involved in this work, and some of them are here. So they appear in the publications. Here is the result of all the experiments that were done. And as we can see, the group one, that is this first group, the group one, in which we have phosphines. These are the best results. So again, we came to the conclusion that the phosphine was the best catalyst for this type of reaction. The work was selected for the cover of one volume of EURGIC. This is the reference. And then that represents, all the work was done in Lisbon, so we wanted to have a symbol of Lisbon. This is the bridge, the 25th of April bridge. And then also joined two groups that are each group in one side of the river. So that was the symbol of this cover. Then I will talk about the second application of this type of complexes. And this is the copper 2. So this first part was all done with copper 1. This second part was done with copper 2. And the reaction is a reverse atom transfer radical polymerization, ATRP, of styrene. So here you have the styrene, the catalyst, copper 2 catalyst, with one radical initiator, which is used very common, which is the IVN, and the polystyrene. The catalyst we use was also based on the BIAN ligand, and they have 2 chlorides, so it was copper 2. This was published in Dalton in 2014, and all these people were, of course, also involved in this work. Polystyrene, well, you all know polystyrene, so here is represented in a tactic way, but usually it's a tactic, and then is used as protective packaging, is used for yogurt containers and for glasses. So it's a plastic that is used very much. And then we did first the synthesis of our compounds. The same, the ligand, also varying the substituents in the aryl group, and doing the reaction with copper Cl2. Copper 2 is paramagnetic, so, but on the other hand, is air stable. So it was easy to manipulate the copper 2 because we could work at air, but on the other hand, identifying the products was more difficult because they were paramagnetic. So we did the reaction, and although we thought that it will be very straightforward, and in this case it was, just simply reacting the ligand with the copper Cl2, we got this compound. When we have the methyl in the substituent, the trimethyl or mesytyl, and then when we did the reaction with the bis isopropyl, then we got an unexpected result. We did the reaction in air, and we got a reduction. So we got a reduction. We isolated this dimer compound, but we had seen before, we had synthesized by another route, but in this case, we got a reduction in air. So we were very surprised, and then finally, we came to the conclusion. We also compare the two ligands, why one doesn't make the reduction and the other one makes the reduction. So we ask people to do the electrochemistry and some theoretical calculations and finally reach the conclusion. But the reason was that the copper salts are very insoluble. So we use methanol to solubilize them. And in this case, the methanol probably reduce the copper to copper 1, and then he gets oxidized to aldehyde. Copper is used also to oxidize alcohols, but that was done without the help or anything and under air conditions. So we finally got the expected one by using another route, and that was done under argon. And then we got both complexes, both monochelated, copper Cl2, and then you have here the structures and the packings, the respective packings of the two compounds. Okay? These two copper-2 compounds, we use them as catalyst for the reverse ATRP of styrene. And then we got these results. For instance, representing ln of m0 over mt, we got a straight line. That means that it's a first-order kinetic. That means that there is always a constant concentration of radical in solution, which is in favor of the reverse ATRP mechanism for the polymerization. This was done using this catalyst, this one, the trimethyl, because was the one that it was found to be active for this kind of catalysis. This compound was not so good, so it was discarded, and we continue with this trimethyl. And the conditions, the trimethyl, and the conditions were styrene, copper, ABN, 201, 0.8, in toluene, 50% volume at 80 degrees centigrade. So in this reaction, this compound acts as catalyst, and also the conversion is represented here. And we compare the experimental squares and plane line, and theoretical triangles and dashed line, dependence of Mn on the synthesized polystyrene on monomer conversion. And we can see from here that the polymerization is controlled from this representation, from these results. So we conclude that we have synthesized a series of mono or bischelated neutral or cationic BIAN copper-1 complexes, and we fully characterize them. All the complexes adopt distorted tetrahedral geometries around the copper-1 centers. All the complexes are active catalysts for the copper-1 catalyzed acid alkene cycloaddition reaction, CuAAC. Best results were obtained for this bis triphenyl phosphine with the 4-isopropyl in the arene. The bischelated complexes are substantially less active than the monochelated ones, and the copper-2 complex with the mesytyl 3-trimethyl exhibited good activity in the reverse atom transfer radical polymerization of styrene. So, well, since copper is related with Venus, I will end up with this picture of Venus. Okay, that's all.
Questions? Have some questions?
Hello, thank you for a nice presentation. I'd like to ask you if you tried your copper-2 complexes in the click chemistry in the presence of reducing argon.
No.
No?
No.
Or in methanol, because it's...
Yes. Yes, I think copper-1 and copper-2 can be used for both reactions. But we adopted this, but we can use copper-2 with a reducing agent for the click, which is being done in the literature. And we can use copper 1, instead of the reverse ATRP, the ATRP, there is an equilibrium. So we can start with copper 1 and do the ATRP, or start with copper 2 and do the reverse ATRP. We change the conditions. So I think copper is used very much because it goes easily from one oxidation state to another. And it's clean, the oxidation is easy to undertake. So this is, for instance, for ATRP, there is a lot of literature on this copper. It's one of the systems that had been most used, and for click also. There is a lot of, okay.
Can you explain a little better the mechanism of the catalytic action? I mean, why is it?
Which one? The first one, the click?
Well, both.
Both, yeah. Well, the first one, we don't know. We didn't look at the mechanism. We didn't look, but what we propose in the first one, since the bichelated has less activity than the monochelated, we propose the first step, the dissociation of the ligand. This is the only thing. We didn't.
You can't go further.
Sorry?
You can't go further.
No. We could go further, but we didn't have this objective at that time. But it could be very interesting, of course, because I don't think there is much done on the mechanism.
It's a very old problem. I remember in the 1960s, there's already a lot of speculation about the mechanism of these copper catalysis. And I still wouldn't be able to explain to a student how it really works.
Yes. I think, yes, for the organic, this is a very important reaction, no? Yes. Yes, and it's regarded as the best click reaction known. This is what I heard in the literature, what I saw.
Excuse my ignorance. What's the solubility of these complexes? I mean, in the reaction medium, they are
Soluble.
solid.
Yes.
They're solid.
No, soluble.
They're solid.
Yes, we do it always in solution. Yes, homogeneous catalysis is all in solution. Yes.
I still remember Professor Huske lecturing about
Yes.
things he just
Yes.
discovered.
Yes.
What's the solvent and if it is done in air or not?
Not this one, the second part.
This one.
No, this one is not done in air. Copper 1 is always done under argon or nitrogen.
Yes, but maybe there would be a redox reaction, something. So that's why I asked.
Yes, no, it's done.
Solvent was,
And the solvent is, I think, is THF. And it's followed by NMR. Hmm?
You said you followed the reaction by animal, but you didn't notice any kind of shifting or blotting of things.
I think we follow mainly the appearance of the products. No, I mean, you mean if there is copper 2, there will be some broadening of the signals.
You verified that by
I think there was not copper 2. It could be followed quite easily by NMR. So there was copper 1.
yes, but you can still check this by evidence.
Yes.
Now you can take NMR from cover 2 without any much.
Yes, but you should see the broadening, no?
Yes,
Yes.
you see the shape.
Yes. Yes, I know. We had some copper 2 NMR also in the other, but it's different. Yes.
More questions?
Just to say that the CKM members at school really enjoyed your talk and they send saludos.
Okay, thank you.
Excellent again.
Okay, thank you.